Today in this video, I'm going to show you how much time it takes to go to Mars from the Earth. And this image that I showed you just now is possibly the worst way you can imagine of going from Earth to the Mars. Because of course all the planets are revolving around the Sun and keep moving from their places. The simplest orbit, which takes the least amount of energy and comparatively needs less amount of propellant, is called the Hohmann transfer orbit. And instead of going directly to the other planet, we take this route. Before we start, I need to explain a few terms to you which are aphelion, the point in the orbit where the planet or satellite is farthest from the Sun, and perihelion, where it's closest to the Sun, and another term related to an ellipse called semi-major axis, which is half the length of the major axis. So now back to the main topic. In the beginning, the velocity of the rocket is equal to that of the Earth, and it's of course in the same orbit as that of the Earth. During the liftoff, the rocket gets an additional velocity in the tangential direction to the Earth's motion, which pushes it out of the Earth's orbit and into a new orbit whose aphelion, that is the farthest point, will be near the orbit of Mars. And of course, I hope you know that everything is revolving in an ellipse and not in a circle. Getting to the planet Mars, rather than just to its orbit, requires that the spacecraft must be inserted into the interplanetary trajectory at the correct time, so it will arrive at the Martian orbit when Mars will be there. This task might be compared to throwing a dart at a moving object. You have to lead the aim point by just the right amount to hit the target. The opportunity to launch a spacecraft on a minimum energy transfer orbit to Mars occurs about every 25 months or every 2 years. Now talking about the main point, which is calculating how much time it takes to reach Mars. We can calculate this by using Kepler's third law of planetary motion, which states that the square of time taken is proportional to the cube of the semi-major axis, or t square equals a cube times some constant. Here a is the semi-major axis, which is half the distance between these 2 points called the aphelion and perihelion. And it's easy to find the semi-major axis because we know that the satellite is closest to the Sun when it's on Earth and farthest when it's in Martian orbit. So a equals to the sum of distance between Earth and Sun and Mars divided by 2. And all these units are in astronomical units, which is defined as the distance between the Sun and the Earth. The time required is just the square root of the cube of the semi-major axis. Putting the values and using a calculator, we get the time is approximately equal to 1.47 years. But the time we just calculated is the time required for the full round trip along this elliptical orbit of our satellite. And to get to Mars, we'll need just half the time, which is about 0.7 years, or you can say 8 months. In the real world, it ranges from 6 to 8 months because here we have ignored the gravitational effects of the other bodies like Jupiter and also the relativistic effects, which are quite negligible.